Uh, Good evening, everyone. My name is Nagmohan Reddy. My teammates are Nitin and Gangava Patil. Our project title is Automatic Kannada Speech Recognition. We are doing this project under the guidance of Dr. Pushpa Mohan ma'am. Let's go with abstract. Automatic speech recognition is the technology that allows the human being to use their voice to speak with computer interface in a way that its most sophisticated variation, normal human conversations. Automatic speech recognition is an area of research that deals with the recognition of speech by machines in several conditions. Most of the people in the village of Karnataka don't know the English language, so a system must build to recognize and understand the Kannada language. This is the outline of our PPT. Let's go with introduction. Kannada is a language spoken in India, predominantly in the state of Karnataka, and is spoken by about 60 million speakers. This language is also spoken in neighbor states like Maharashtra, Tamil Nadu, and Andhra Pradesh. Automatic speech recognition can be defined as the independent, computer-driven transcription of spoken Kannada language into readable text in real time. ASR system. Automatic speech recognition is a technology that allows a computer to identify the words that a person speaks into a microphone or a telephone and convert them to a written text. Further, Gangava Patil will be explained.
Yeah, good evening all. Now coming to the problem statement, our aim is to build an end-to-end ASR system to recognize continuous Kannada speech sentences and to help the people who don't know English to use this application. And relevance of the problem, our motivation is to develop a system that should recognize and translate the Kannada speech efficiently and should efficiently recognize speech in a noisy environment. And our objective is to develop a continuous Kannada speech recognition system using machine learning algorithms. Further, Nitin will explain.
Yeah, good evening, everyone. My name is Nitin. I'll be continuing with the proposed system. This is the architecture of our project. First, coming to the data set, we have collected 2,500 data sets in which we have divided into test and train data sets, and we have augmented the data set. For the augmentation, we have used the three features. That is, we have added the noise to the data set, and we have changed the pitch of the data, and we have stretched the time. After that, the augmented data set as an input will be given for the signal processing, and we'll be extracting the features using the MFCC, in which we'll be applying the discrete Fourier transform and log and inverse log. By that, we'll as an output we will be getting the feature matrix. And for the pattern recognition, we'll be using the decoder, which will be built using acoustic and language model. Development tools. We have coded in the Colabs and we have used PyTorch. Coming to the implementation. First, we'll be needing the we'll need GPU. So we'll be checking if the GPU is available or not, and we'll be printing the GPU information. And we'll be installing all the requirements, that is datasets, transformers, torch audio. Now we need to prepare the data tokenizer and we need to extract the features. First, we'll be loading all the data sets. For that, we'll be mounting the Google Drive to the Colabs, and then I'll be printing all the file names. That is nearly 2,500 data sets. In that, I will be splitting for the test and training data sets. For the training data, I have taken 1,500 data sets, and for the test, 1,000 data sets I have taken. And I'll be removing all the special characters from the data sets and we're printing this. Next, I'll be mapping all the characters to the numbers 0 to 65. And I'll be storing in the JSON file, and I'll be loading that loading the JSON file into the model. Now for the wave 2 vector tokenizer, ASR model maps the speech signal to a sequence of context representation. For the speech recognition, the model has to map the sequence of context representation to its corresponding transcription, which means that the linear layer has to be added on the top of the transformer block. This linear layer is used to classify each context representation to a token class analogies to how a linear layer is added onto the breadth embedding for further classification after the training. And the output size of this layer corresponds to the number of tokens in the vocabulary, which does not depend on the XLS as training task, but only on the label data sets used for the fine tuning. So in the first step, we'll take a look of the chosen data set. And define the vocabulary. And for defining the vocabulary, we'll be using this, and we'll be using the mapping function. So it is defined here, and we'll be storing this in the JSON file. Next. And for the feature extraction, we'll be needing, we should need the data, that is speech data with a 16,000 kilohertz frequency. So we'll be resampling that using this code. After the resampling, we'll be using the feature extractor for extracting the features. Next, we'll be preparing the data set. After preparing the data set, we should train the model. The data is processed so that we are ready to start setting up the training pipeline. And we should define a data collector. In contrast to most NLP models, the XLRS has a much larger input length than the output length. For example, a sample of input length of 50,000 has an output length of no more 100. Given the larger input sizes, it is much more efficient to pad the training batches dynamically, meaning that all the training samples should only be padded to the longest sample in the batch and not the overall longest sample. Therefore, fine-tuning ASR requires a special padding data collateral, which we'll define below. And next, we should set up the trainer. This is a code. And here we'll be defining the data collateral. The code for data collateral is here. In contrast to the common data collectors, this data collector treats the input values and labels differently and thus applies to separate padding functions on them. This is necessary because in speech input and output are of different modalities, meaning that they should not be treated by the same padding functions. Next, the evaluation matrices is defined. We'll be using the word error rate. And now we can load the train checkpoints of the wave 2 vector to XLSR300M. The tokenizer pad token ID must be to define the model's pad token ID. And the first component of XLSR consists of a stack of CNN layers that are used to extract acoustically, meaningfully, but contextually independent features from the raw speech signals. And we'll be using the feature extract features here. And we'll define all the parameters related to the training. And we'll be using group by length and learning rate YDK. Group by length makes training more efficient by grouping training samples of similar input length into one batch. This can significantly speed up training time heavily by reducing the overall number of useless padding tokens that are passed through the model. And learning rate and YTK were heuristically tuned until fine tuning has become stable. And now all the instances can be passed to the trainer, and we are ready to start training. And we'll start training by using this command trainer.train, and it will take some time to train the model. And after that, we can see here the training loss and the validation word error rate goes down nicely. We can see for the first 400, the training loss is nearly 3.8 and word error rate is 0.69. As we can see that increasing the steps, the training loss and the word error rate comes down to 0.04 and 0.3 respectively. And as I said, we have used nearly 1,600 data sets for the training. And next, coming to the testing part, we have used a word error rate. First, we'll be loading our trained models, which I have saved in the Google Drive. Next, I'll be passing all the testing data, which I mounted the Google Drive and collected all and loaded all the data into the Colabs. Next, I'll be using this testing data set. These are all the results I have got. And for the calculating, and after calculating the word error rate, I have got a 40. The word error rate is 40. And coming to the evaluation part or validation part, first we'll be loading the models. Then I'll be defining the two functions using the model for the Now for the validation part, first we'll record our voice, and then we'll be using these two functions, that is transcription and translation, for checking the output. First, I'll be recording my voice. Rama hodanu, Site hodalu. Once we'll check the audio. Rama hodanu, Site hodalu. Now I'll transcript it using the model. Yeah, we are getting Rama hodanu and Site hodalu, which is correct. And now we'll translate it to English. Yeah, Rama is gone and Sita is gone. Yeah, now we are getting the same correct output. Next, Nagamohan Reddy will continue.
Conclusion. A lot of work is done in automatic speech recognition system for English language, but not for Indian language. Since the last decade, Indian researchers are focusing on developing automatic speech recognition system for Indian languages. But to date, no successful ASR systems are commercially available for most Indian languages. In this paper, we discuss a brief history of automatic speech recognition system, the architecture of automatic speech recognition system, different feature extraction techniques and various approaches and pattern recognition, automatic speech recognition system, and some research done date on regional language in India. Thank you.
Now for the validation part, first we'll record our voice, and then we'll be using these two functions, that is transcription and translation, for checking the output. First, I'll be recording my voice. Rama hodanu, Site hodalu. Once we'll check the audio.
Rama Hodanu, Site Hodanu.
Now I'll transcript it using the model. Yeah, we are getting Rama Hodanu and Site Hodadu, which is correct. And now we'll translate it to English. Yeah, Rama is gone and Sita is gone. Yeah. Now we are getting the same correct output.